හරි පුතේ. අපි unit 12 ionic equilibrium වලට move වෙනවා. Unit 12 equilibrium ionic equilibrium. Acid base titrations. Right. Unit 12 ionic equilibrium, acid base titrations. Okay. Right. Basically acid base titrations විදියට we study strong acid, strong base titrations, strong base, weak acid titrations, strong acid, weak base titrations, and the fourth one, weak acid, weak base titrations. The fifth one, CO3 2 minus HCl titration. So basically we study about 5 different types of titrations in ionic equilibrium, right? Basically we study about 5 different types of titrations in ionic equilibrium. Okay, so even you don't have equilibrium reactions, in strong acid, strong base titrations. We study strong base, strong acid titrations under ionic equilibrium, right? In strong acids and strong bases, you don't have equilibrium reactions, but still we study that under acid base titrations, right? Right, පුතේ ලියා ගන්න. හරි පුතේ. බලන්න. Then strong acid strong base titrations, that is the subtopic. Strong acid strong base titrations, strong acid strong base titrations. Strong acid strong base titrations. Strong acid strong base titrations. Right. So what are the examples for strong acids? HNO3 nitric acid we consider as a strong acid. Sulfuric acid H2SO4 we consider as a strong acid. Hydrochloric acid HCl, hydrobromic acid HBr, and hydroiodic acid, these 5 acids considered as strong acids, right? Strong acids. What are the strong bases? Lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide, barium hydroxide, strontium hydroxide, calcium hydroxide. These 8 bases are generally considered as strong bases, right? එතකොට strong acids generally 5 strong acids and 8 strong bases, right? So strong acids and strong bases, right? පුතේ ලියාගන්න. Hari. So I'll take an example of strong acid strong base titration. Strong acid strong base titration. Strong acid strong base titrations, right? So you have point 0.3 moles per cubic decimeter, 0.3 moles per cubic decimeter, 0.3 moles per cubic decimeter, HCl solution, and you take 25 cubic centimeters from that solution, right? So you have 0.25 cubic centimeters of 0.3 moles per cubic decimeter HCl solution in a titration flask, right? In a titration flask, and you titrate that solution by using 0.3 moles per cubic decimeter sodium hydroxide solution, right? You titrate that solution by using 0.3 moles per cubic decimeter sodium hydroxide solution, right? So that is the example we consider for the strong acid strong base titrations, right? Strong acid strong base titrations, right? Right. පුතේ අපි මේක චුට්ටක් අඳගමු. හරි පුතේ ලියා ගන්න. 25 cubic centimeters of 25 cubic centimeters of 25 cubic centimeters of 0.3 moles per cubic decimeter. 25 cubic centimeters of 0.3 moles per cubic decimeter. 0.3 moles per cubic decimeter. HCl solution. HCl solution is titrated. 25 cubic centimeters of 0.3 moles per cubic decimeter. 25 cubic centimeters of 0.3 moles per cubic decimeter. 0.3 moles per cubic decimeter. HCl solution. HCl solution taken into a titration flask. Taken into a titration flask. Taken into a titration flask. Is titrated. Is titrated. Is titrated against. Is titrated against 0.3 moles per cubic decimeter. 0.3 moles per cubic decimeter. 0.3 moles per cubic decimeter. Sodium hydroxide solution. Sodium hydroxide solution. Sodium hydroxide solution taken into the burette. Taken into a burette. Taken into a burette. I balana පුතේ 25 cubic centimeters අප බලන 25 cubic centimeters of 0.3 moles per cubic decimeter. 0.3 moles per cubic decimeter HCl solution. HCl solution taken into a titration flask. Taken into a titration flask was titrated. Was titrated from was titrated with 0.3 moles per cubic decimeter. 0.3 moles per cubic decimeter sodium hydroxide solution. Sodium hydroxide solution. Sodium hydroxide solution sodium hydroxide solution taken into a burette, right? Taken into a burette, right? Okay. The question එකට දාගන්න question number 1 කියලා. sorry ඒකට number 1 දාගන්නකෝ. number 1 දාගන්න. And simple Roman number 1. Simple Roman number 1. Calculate the pH. Question එක. Calculate the pH calculate the pH of the titration flask, calculate the pH of the titration flask, calculate the pH of the titration flask, calculate the pH of the titration flask at the beginning of the titration, at the beginning of the titration, calculate the pH of the titration flask, calculate the pH of the titration flask at the beginning of the titration, at the beginning of the titration, at the beginning of the titration. So, what do you mean by pH? pH is a scale to introduce H plus concentration present in an aqueous solution, right? pH is a scale, right? pH is a scale we use to express H plus concentration, right? H plus concentration present in an aqueous solution, right? So the definition for pH is minus log 10 to the base H3O plus concentration, right? Minus log 10 to the base H3O plus concentration. So that is the definition of pH, right? And to calculate pH, right? To calculate pH of a particular solution, you need H3O plus concentration, that is H plus concentration, right? H3O plus concentration, or else that is what you called as H plus concentration, right? To calculate pH of any solution, you need H3O plus concentration in a particular solution, right? Okay, right. pH की नेकर definition निकल लिया अगर hari putih මේ ලියා ගන්න. To calculate pH, of a particular solution, to calculate the pH of a particular solution, to calculate the pH of a particular solution, H3O plus AQ concentration, H3O plus aqueous concentration, H3O plus aqueous concentration has to be calculated. At the beginning of the titration, at the beginning of the titration, at the beginning of the titration, there is a HCl solution, there is a HCl solution with the concentration of, there is a HCl solution with the concentration of, with the concentration of 0.3 moles per cubic decimeter. There is a HCl solution with the concentration of 0.3 moles per cubic decimeters. 0.3 moles per cubic decimeters. Right. Putih balana. Enang at the beginning of the titration, at the beginning of the titration, you have a HCl solution. You have HCl solution with the concentration of 0.3 moles per cubic decimeter. Right. At the beginning of the titration, you have HCl solution with the concentration of 0.3 moles per cubic decimeters. So HCl solution, HCl aqueous solution HCl solution in HCl solution you have H plus aqueous and Cl minus aqueous, right? So HCl, that is hydrochloric acid, is a strong acid. What do you mean by strong acid? It is exists as completely dissociated ions, right? Hydrochloric acid HCl aqueous is a strong acid. Because of that, HCl exists as completely dissociated form, right? Completely dissociated ions. HCl exists as completely dissociated ions. H plus aqueous ions and Cl minus aqueous ions. So this is what you called as a strong acid. Strong acid exists as a completely dissociated ions, right? Strong acid exists as a completely dissociated ions, right? Then the concentration of HCl 0.3 moles per cubic decimeter, if it exists as completely dissociated ions, if it exists as completely dissociated ions, you have 0.3 moles per cubic decimeter H plus aqueous and you have 0.3 moles per cubic decimeter Cl minus aqueous, because it is completely dissociated. HCl is a strong acid and it is exists as completely dissociated ions. Stoichiometry, that is molar ratio, is 1:1:1. So 0.3 moles of HCl solution exists as completely dissociated 0.3 moles per cubic decimeter H plus aqueous and 0.3 moles per cubic decimeter Cl minus aqueous, right? Putih lihat. හරි පුතේ මෙම ලියා ගන්න. HCl equal HClAq is a strong acid. HClAq is a strong acid. HClAq is a strong acid and exists as completely dissociated H plus AQ and Cl minus AQ ions. H plus AQ and Cl minus AQ ions. Right, පුතේ බලන්න. Now we have the concentration of H3O plus. We have the concentration of H3O plus. H plus aqueous concentration equal H3O plus concentration. දෙන්නම එක්කිනා. Right. H plus AQ concentration equal H3O plus concentration equal 0.3 moles per cubic decimeters, right? 0.3 moles per cubic decimeters. And we know that pH is equal minus log 10 to the base H3O plus aqueous concentration, H3O plus aqueous concentration, that is what you called as pH. Right, pH equal minus log 10 to the base 0.3 moles per cubic decimeter. පුතේ 0.3 moles per cubic decimeter කියන එක I can write as 3 into 10 to the power minus 1 කියලා. Right, 3 into 10 to the power minus 1 කියලා. එතකොට 1 decimal place taken into your right hand side, 1 decimal place taken into your right hand side, so the value is increased from, right, the value is increased, then the 10 to the power has to be a minus value, because you can't increase a value, right? Make a 0.3 can a 0.3, you can't increase it. Even you write that as a 10 to the power value, still you should have the same value. Enang 10 to the power value එකෙන් again මේ value එක reduce කරන්න ඕන, right? 10 to the power value එකෙන් ආපහු value එක reduce කරන්න ඕන. එතන decimal place එක scientific notation එකට ගනිද්දි 1 decimal place right ගන්නවම, right, 1 decimal place into your right hand side කියන්නේ 3 into 10 to the power minus 1, right, 3 into 10 to the power minus 1. Or else you can write this as 3 over 10 kilo. 0.3 can be written as 3 over 10 kilo, which means this is equal, මෙතන තියෙන්නේ නම් 10 to the power 1 එකක්, එහෙනම් එයා උඩට ගන්න 3 into 10 to the power minus 1, okay, 3 into 10 to the power minus 1, right. So the H3O plus concentration can be written as 3 into 10 to the power minus 1 3 into 10 to the power minus 1, right? 3 into 10 to the power minus 1 H3O plus concentration is 3 into 10 to the power minus 1. Then log 3 multiplied by, right? So here you have a multiplication, right? Here you have a multiplication. I can write this as pH equal minus log 10 to the base 3 multiplication එකක් plus minus log plus minus log 10 to the base 10 to the power minus 1 because it is a multiplication, right? පුතේ log 3 කියන එක you can take from a logarithm table, but it is better if you can remember log values for 2, right? 2 වෙනකොට දෙකේ log එක 2 වල log එක 0.3010 කියලා. If you can remember, it is easy for calculations. එහෙනම් log 23010 කියලා you can remember. 3 එක log 3 එක 0.4771 කියලා you can remember. 2344 කියන එක you can take as 2 multiplied by 2, which means 0.3010 plus 0.3010 කියලා you can take, right? Because log වල multiplication එකක් කියන්නේ sum එකක්, right? So you don't need to remember this. Log 5 එක you can remember 0.699. Likewise මේ වගේ small logarithm values you can 2357, right? 2357 logarithm values, if you can remember 2357, then it is easy for your calculations. Now log 3 එක පුතේ මම ගන්නවා 0.4771, log 3 එක 0.4771, and you have a minus sign here, so minus 0.4771 plus log 10 to the base 10 to the power minus 1, 10 to the power value එකක් log වලදී එහෙම එනවා. log 10 to the base 10 to the power minus 1 කියන්නේ minus 1, log 10 to the base 10 to the power minus 1 කියන්නේ minus 1 multiplied by minus sign, so you get plus 1, right? You get plus 1. එහෙනම් මෙයාගේ simplification එක you get 0.5229. So that is how you calculate a pH value, right? 0.5229. That is how you calculate a pH value, right? Right. පුතේ ලියා ගන්න. හරි පුතේ. එතකොට we have H3O plus concentration, right? This is how you calculate a pH value, right? This is how you calculate a pH value. You substitute H3O plus concentration, right? Okay, right. Simple Roman number 2. Simple Roman number 2. Simple Roman number 2. Log 2 කියලා කියන්නේ 0.3010. log 3 කියලා කියන්නේ 0.4771. log 5 කියලා කියන්නේ log 5 කියලා කියන්නේ 0.699. log 7 කියලා කියන්නේ 8153. Sorry. Right. Okay. Roman number 2. Calculate the pH. Calculate the pH. Calculate the pH at the equivalence point. Calculate the pH at the equivalence point calculate the pH at the equivalence point of the above titration. Calculate the pH at the equivalence point of the above titration. Calculate the pH at the equivalence point of the above titration. So what do you mean by equivalence point? Equivalence point means whatever the reagent present in your titration flask is completely neutralized, right? In an acid-base titration, you have either an acid or base, so it is neutralized with the solution present in the burette, So equivalence point of a titration is, right, equivalence point of a titration means, equivalence point of an acid base titration, right? Whatever the titration, right, equivalence point of of a titration means the solution present, right? The solution present is completely reacted with the solution added from the burette, right? The solution present in the titration flask is completely reacted with the solution added from the burette, right? With the solution added from the burette. So that is what you called as equivalence point, right? That is what you called as equivalence point, right? right. පුතේ ලියා ගන්න. Solution present in the solution present in the solution present in the titration flask the solution present in the titration flask is completely neutralized. The solution present in the titration flask is completely neutralized. Is completely neutralized. Is completely neutralized. Is completely neutralized. From the solution added, from the solution added, from the solution added, from the solution added of the burette, from the solution added of the burette of the burette at the equivalence point, at the equivalence point of an acid base titration, of an acid base titration, equivalence point of an acid base titration. Equivalence point of an acid base titration. හරි පුතේ බලමු. So this is the reaction. HCl present in the titration flask is completely neutralized from the sodium hydroxide added from the burette, from the sodium hydroxide added from the burette. So ionic equilibrium, right, is classified under physical chemistry, right, is classified under physical chemistry. So you should write physical states of each chemical species, right? You should write physical states of each chemical species, right? Each chemical species. Right. HCl aqueous plus sodium hydroxide, right, that is the reaction. So initially you have hydrochloric acid in the titration flask. Initially you have hydrochloric acid in the titration flask. Then I can calculate initial amount. I can calculate initial amount. I can calculate initial amount. So initially you have HCl in the titration flask. So 0.3 moles per cubic decimeter, 0.3 moles per cubic decimeter HCl solution is present in the titration flask, and you have 25 cubic centimeters. You have 25 cubic centimeters from that. So, how do you calculate the initial amount? Amount means moles. You use N equals EV. You use N equals EV. Amount equal concentration into volume. Amount equal concentration into volume. N equals EV. So here you have the concentration 0.3 moles per cubic decimeter, and here you have the volume 25 cubic centimeters, but cubic centimeters convert karandona cubic decimeters वलट because concentration term में का 0.3 moles per cubic decimeters, right, cubic decimeters. So cubic centimeters cubic decimeters वलट convert karanda 10 to the power minus 3 वली it has to be multiplied, right, 25 into 10 to the power minus 3. Then 25 into 3 means 75, 1 decimal place, then 7.5. So the amount is 7.5 into 10 to the power minus 3 moles. So this is the initial amount of HCl, right? This is the initial amount of HCl. Initially you will have sodium hydroxide. Initially you will have sodium hydroxide. Then I can calculate and you add sodium hydroxide for the neutralization. You add sodium hydroxide for the neutralization. Then added amount. Added amount. Added amount. HCl, you do have you are not adding HCl. So this is an equivalence point. If this is an equivalence point, the amount present in the titration flask, has to be neutralized because it is equivalence point, right? The amount present in the titration flask has to be neutralized because it is an equivalence point, okay? It is an equivalence point. So the amount present in the titration flask is 7.5 10 to the power minus 3. The stoichiometry of this reaction, which means the molar ratio of this reaction is 1:1. Molar ratio of this reaction is 1:1. Then 7.5 into 10 to the power minus 3 moles HCl තියෙනවා. It has to be neutralized from sodium hydroxide. So 1:1 stoichiometry now, same amount of base has to be added. Same amount of base has to be added, right? 7.5 10 to the power minus 3 has to be added because stoichiometry 1:1, right? So that is the added amount. Then reacted amount. So you have 7.5 10 to the power minus 3 moles of HCl and 7.5 10 to the power minus 3 moles of sodium hydroxide. They have equal amounts because this is an equivalence point. So it is completely neutralized. So the reacted amount 7.5 into 10 to the power minus 3 moles of this is neutralized with 7.5 10 to the power minus 3 moles of this, right? Because it is equivalence point, right? It is equivalence point. Then the final amount 7.5 10 to the power minus 3 HCl is there at the beginning of the titration in the titration flask, right? 7.5 10 to the power minus 3 moles of HCl is present in the titration flask at the beginning of the titration, and the same amount of sodium hydroxide is added because it is the equivalence point, right? It is the equivalence point. So it is completely neutralized because it is the equivalence point. So you do have 7.5 10 to the power minus 3, 7.5 10 to the power minus 3. Initially you have this and reacted amount take this. So it is completely neutralized, no more acid, and this is the added amount and this is the reacted amount, no more acid. But these two react together in 1:1 stoichiometry, so you get NaCl aqueous, you get NaCl aqueous, so the final amount has to be equal, right? 1:1:1:1, that is the stoichiometry, right? 1:1:1:1, that is the stoichiometry. So that is the molar ratio they have reacted, so you get the same amount of NaCl 7.5 10 to the power minus 3 and 7.5 10 to the power minus 3 of each, right? Okay, so this is how they have reacted together. This is how they have reacted together, right? Put away when I can හරි පුතේ මේව ලියා ගන්න. Amount present in the titration flask. The amount present in the titration flask is completely neutralized. Amount present in the titration flask. The amount present in the titration flask is completely neutralized. Is completely neutralized because the amount present in the titration flask is completely neutralized because it is the equivalence point. It is the equivalence point. Equivalence point of the titration. Therefore, the only chemical species present in the titration flask, the only chemical species present in the titration flask, the only chemical species present in the titration flask is the salt. Is the salt. Is the salt NaClAq. The only chemical species, the only chemical species present in the titration flask, the only chemical species present in the titration flask is the salt NaClAq. NaClAq. That is the only chemical species present in the titration flask. NaClAq, right? NaClAq. Okay. Right. NaClAq is the only chemical species present in the titration flask. That is sodium chloride. Okay. That is sodium chloride. Sodium chloride exists in aqueous solution as Na plus Aq and Cl minus Aq because it is a sodium salt, right? It is a sodium salt. All the sodium salts, right? All the sodium salts are completely dissociated in their aqueous solutions, right? All the sodium salts are completely dissociated in their aqueous solutions. Not only that, Na plus, K plus, rubidium, Rb plus, cesium, Cs plus, sodium, potassium, rubidium, cesium, all these salts exist as completely dissociated ions, right? All these salts exist as completely dissociated ions. All these salts exist as completely dissociated ions. All these salts exist as completely dissociated ions. Right? All these salts exist as completely dissociated ions. Right? All these salts exist as completely dissociated ions. Right? All these salts exist as completely dissociated ions. Right? All these salts exist as completely dissociated ions. So source of Na plus, K plus, Rb plus and cesium plus, sodium, potassium, rubidium, cesium, they exist as completely dissociated salts, right? Then all the salts of NO3 minus, NO2 minus, HCO3 minus, all the salts of NO3 minus, NO2 minus and HCO3 minus and CH3COO minus, CH3COO minus, they exist as completely dissociated ions, source of potassium, right? Source of sodium, source of potassium, source of rubidium, source of cesium, source of nitrate, source of nitrite, source of bicarbonate, source of acetate, right? All these sources exist as completely dissociated ions in their aqueous solutions, right? They are highly soluble and they exist as completely dissociated ions. For example, sodium carbonate, sodium sulfate, sodium sulfide, sodium chloride, sodium iodide, sodium bromide, sodium bicarbonate, sodium phosphate, sodium hydroxide, whatever the sodium salt is completely dissociated in their aqueous solution. They exist as ions in their aqueous solutions, not as compound, right? All the sodium salts, so all the salts of sodium, potassium, rubidium, cesium, all the salts of NO3 minus, NO2 minus, HCO3 minus, CH3COO minus, they exist as completely dissociated ions, right? Completely dissociated ions, right? So my point is, sodium chloride is the salt here and it exists as completely dissociated ions in their aqueous solution, right? It exists as completely dissociated ions in their aqueous solutions, right? Completely dissociated ions in their aqueous solutions. So pH of the solution, right? Now it is a sodium chloride solution, right? Now it is a sodium chloride solution. To calculate the pH of the solution, you have to consider this salt solution, this sodium chloride solution, right? So that is my point, right? പുതിയ വരികളിയാകും Right. පුතේ මේම ලියා ගන්න. The equivalence point of any acid base titration of any acid base titration is a salt solution. Is a salt solution. Is a salt solution. Is a salt solution. pH of a salt solution, pH of a salt solution is determined by based on acid hydrolysis, based on salt hydrolysis, based on salt hydrolysis. Based on salt hydrolysis. Based on salt hydrolysis. Based on salt hydrolysis. Right, පුතේ වෙනම ලියන්න. Source of Na plus, comma K plus, comma Rb plus, comma Cs plus, and NO3 minus, comma NO2 minus, comma HCO3 minus, comma CH3COO minus, NO3 minus, NO2 minus, HCO3 minus, CH3CO2 minus, CH3CO2 minus exist as completely dissociated ions, in their aqueous solution. their aqueous solutions. Right. Then, so to calculate the pH of sodium chloride solution, you should consider about salt hydrolysis, right? You should consider salt hydrolysis. I have explained that sodium chloride is the salt present in this titration, right, in the equivalence point. Sodium chloride is the salt present in the equivalence point of this titration, and it exists as Na plus aqueous and Cl minus aqueous. Here Na plus is a salt, Na plus is a cation of strong base. Na plus is a cation of strong base. It is a cation derived from a strong base. Na plus is a cation derived from a strong base. Cl minus is an anion derived from a strong acid. Na plus is a cation derived from a strong base, and Cl minus is an anion derived from a strong acid, right? Is derived from a strong acid. Cations are derived from a strong base, doesn't further hydrolyze in water. Cations are derived from a strong base, right? A cation derived from a strong base doesn't further hydrolyze in water. It is neutral. An anion derived from a strong acid doesn't further hydrolyze in water. Strong base sodium hydroxide. Na plus is derived from strong sodium hydroxide. It's a strong base. Strong acid HCl, strong acid. HCl, strong acid. So, a cation derived from a strong base doesn't further hydrolyze in water, and an anion derived from a strong acid doesn't further hydrolyze in water. They are neutral in their aqueous solution. Therefore, this salt also a neutral salt, right? This salt also a neutral salt. So this solution is a neutral solution. This solution is a neutral solution. Right. Put your liagan. right පුතේ මේව ලියා ගන්න. Na plus aqueous, Na plus AQ, Na plus AQ, Na plus AQ, Na plus AQ is a cation derived. Is a cation derived from a strong base. Is a cation derived from a strong base. Is a cation derived from a strong base. A cation derived from a cation derived from a cation derived from a cation derived from a strong base. A cation derived from a strong base doesn't further hydrolyze in their aqueous solutions. Doesn't further hydrolyze in their aqueous solutions. Doesn't further hydrolyze in their aqueous solutions. Therefore, it is a neutral cation. 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 වෙනම ලියන්න. Cl minus AQ is an anion derived from a strong acid. Is an anion derived from a strong acid. Derived from a strong acid. Anions derived from an anion derived from a strong acid. An anion derived from a strong acid doesn't further hydrolyze in water. 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 Therefore, Cl minus Aq, Cl minus Aq is a neutral anion, and finally NaClAq is a neutral salt. NaClAq is a neutral salt. NaClAq is a neutral salt. Therefore, this is a neutral solution. Therefore, this is a neutral solution. Wait, Maliana. pH of a neutral solution, pH of a neutral solution is determined by 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 the salt hydrolysis. pH of a neutral solution is determined by auto-ionization of water. pH of a neutral solution is determined by auto-ionization of water. Auto-ionization of water. Auto-ionization of water. Right. So this is what you called as auto-ionization of water. You have H2O liquid, right? Consider H2O molecule present in this solution and it release a proton to another H2O molecule present in this solution, right? Present in this solution. If this H2O molecule release H plus into this H2O molecule, if this H2O molecule release a proton, which means H plus, if this H2O molecule release H plus to this H2O molecule, this one will be converted into hydroxide ion, right? If this H2O molecule release a proton to this H2O molecule, this will convert, it release a proton means H plus release karano, then ekatru it is converted into OH minus and this H2O molecule accept a proton. This H2O molecule accept a proton and it is converted into H3O plus aqueous. H3O plus aqueous. This is what you called as auto-ionization of water, right? This is what you called as auto-ionization of water. This water molecule release a proton, right? This water molecule release a proton. This water molecule release a proton, and this one accept a proton. Releasing a proton is an acidic property, so this is an acid, and accepting a proton is a basic property, so this water molecule act as a base. Water can act as a base as well as an acid, so you call that as amphiprotic. Water is not an acidic compound or a basic compound, it is amphiprotic. It is amphiprotic. Amphiprotic. It can donate a proton and it can accept a proton. It is amphiprotic. Water is an amphiprotic. So, this is what you called as auto-ionization of water, right? This is what you called as auto-ionization of water, right? So, you can write, so this is the equilibrium of water, right? This is the equilibrium of water in any system, right? In any aqueous solution, this is the equilibrium exists in water, right? This is the equilibrium exists in water in any aqueous solution, right? Auto-ionization of water is an exothermic process. Delta H negative. Auto-ionization of water is an exothermic process. Delta H not negative delta H not negative, it is an exothermic process. It is an exothermic process, right? Because it is an endothermic process. Delta H positive, right? It is an endothermic process, right? So this is what you called as auto-ionization of water. So now you can understand, here you have H3O plus. If you can calculate this H3O plus ion concentration, right? If you can calculate this H3O plus ion concentration, you can calculate the pH, right? Right. Put it